Hello and welcome. So today we are going to look at the transitions between different electronic levels or different orbitals, in particularly naphthalene molecule. So for naphthalene molecule, we earlier what we did we took all the 10 p pi orbitals situated in each of the carbon atoms. So total 10 p pi orbitals we took. So we had like phi 1 to phi 10, and we formed the 10 SALCs, right. So this 10 SALCs will give me 10 orbitals essentially, right, and these are all pi type orbitals. So we have now what were those orbitals, and we also got the symmetries of those orbitals. So in the next step we got the symmetries of these orbitals, meaning that particular irreducible representation according to which this SALCs transform as, that we found out. And we also saw that we also used the Huckel's approximation to particularly assign the energies to different orbitals that we found here. So ultimately we got this particular energy diagram. So we can see that there are different orbitals having different amount of energy, and we also use the Pauli's exclusion principle and Hund's rule to arrange this electrons into the particular orbitals, right. So now what we can think of, transition from one particular energy state to another one. Now here altogether I have 10 energy states. Now in principle I can take one electron from any of the given orbital and put it into a higher orbital, right. So thereby I can get an excited state. So but whether that is actually allowed or not, okay, that we need to find out. And we also try to think about a particular transition which is viable within the energy that we can get from normally visible or UV radiation, okay, for our normal spectroscopic techniques. So what is the lowest energy gap that I can think of can have a transition of an electron from a given state to an upper state? So that is obviously, if you look at this picture, is a transition from here to this particular state. That means I am talking about a transition from AU, which is also marked as 1, because there are several there are orbitals with the same symmetry. So to differentiate them, here things are marked by this superscript 1, 2, 3, so on, in the order of increasing energy. All right. So if I have a transition from this A1 AU orbital to B2G orbital, then that will give me the lowest amount of energy. So what will be the energy for this transition? That will be 618. That is the gap between these two states, right? So that will be this, okay. So this will be 0.1236. That will be the energy that in terms of beta. So this is the lowest transition that we can think of. Now what are the other two transitions that I can think of? One is from this particular state to so this particular state to B3G. So I can think of a transition which is AU1 to B3G 2 orbital. Okay. And just note one thing, that I am calling this as orbital because they are orbitals. They are the SALCs that we formed out of the atomic p pi orbitals. All right. So this AU or B3G that we are writing right now, this does not give me the state of, or the electronic state. Okay. So make it clear. So mostly what we actually do, instead of writing them as this capital AU, it's preferred that one writes this in terms of the small letters. So actually, if I want to write this one in a proper way, I should write AU, if I want to mark this one, then to B2G. Okay. And we will use this capital letter for the overall state. Okay. So now if I follow that terminology, then I should write here also it is AU1 to B3G 2. So this transition will will have energy of 1.618, and I can think of another transition from B1U to B2G. So if I write B1U to B2G, that will also have an energy of 1.618. So both of them are having almost similar energy. Now if I want to know whether this three lowest order transitions are allowed or not, if they are allowed, then they are allowed in which polarization. Okay. So that we need to find out. So how to tackle this problem? Like, I have this orbital symmetries, and I know that in case while trying to find out whether a transition is allowed or not, I need to find out the I need to worry about the wave functions, okay, of the particular state. So I need to know how to get the state, the electronic state of this whole system. All right. So let's try to do that. So overall, at first, what we have to do, we have to take one electron from one of these states, and then we have to transfer it here. Okay. So on whatever state I am trying to go to, so we have to transfer the electrons to that particular state. Now, how do we write down the total overall electronic configuration? So the electronic configuration of this existing system, which is the ground state, so I have lower energy to the higher energy. If I write down, then my situation will be B1U. Okay. Now I will use a different symbol. Symbol means here instead of writing those numbers within the parentheses, which dictates that okay, this is a separate BU having a higher energy than the previous B1U. Instead of that, I will use a prime notation to differentiate two different states having the same irreducible representation, and we will use a superscript to indicate the number of electrons in that particular orbital. So this B1U orbital, it has a pair of electrons, so I will write B1U2, and then next comes B2G 2, B3G 2, B1U 2. Now you see B1U already exists here, right? So I will separate them by using a prime, and then at last I have AU 2. All right. Now all this electrons are paired up, right? So in each orbital I have two electrons. Now each electron has a symmetry of that particular orbital, correct? So the overall state of that particular orbital, if I forget that I have any other orbital, so I am considering, say, suppose B1U, this particular orbital, okay. So B1U has 2 electrons, so each electron has the symmetry B1U. So if I have to describe the state of the system of that, say, one orbital system having a pair of electrons, then it will be the direct product of those symmetries of each electrons. So therefore I will have B1U and direct product between 2 B1U. So I will have a situation like B1U, B1U, and what will be the result? I know if 2 irreducible representation, the square of the irreducible representation will contain the totally symmetric IR, and here in this case, since they are one dimensional, I can directly say that this will be the totally symmetric irreducible representation, that is A1G for the particular point group, that is D2H. Okay. So this I said about one of the orbitals. Now if you think that you have 5 different orbitals, each one of them have 2 electrons each. So for all of these orbitals, if you do this direct product, overall you will get the symmetry of the state. So essentially what you have to do, you have to do like B1U cross B1U, okay, then you have to get B2G, B2G, and so on. Okay. Now in each one of them is giving totally symmetric IR. So altogether, since all of the orbitals are occupied by 2 electrons, then overall the state of the system, that is electronic state of the system, is totally symmetric, right? So here for D2H, if I look at, so this is totally symmetric IR is AG, right? So if this is my configuration at the ground state, which it is, so the ground state has the symmetry of AG, right? And we also now know that if the configuration has all electrons paired up, then I can easily ignore and I can only concentrate on the portion which or the orbitals which contain unpaired electrons. So I should be worried about only those, but others will always give you totally symmetric irreducible representation. So my this is my ground state. Now we have to worry about the excited state. So the excited state, which one? So first we have to worry about this lowest energy transition, right? So that is from A1U to B2G, right? So A1U to B2G, if I make a transition, so what I can do, I can take one of these electrons from here and I can transfer it here, right? So I will have, instead of here, I'll have it here. Now I have to find out what is the electronic state of, or what is the symmetry of this state, okay, right? I am taking the electron from this orbital to this orbital and getting a state. So first, when I had all the system paired up, in this particular case of naphthalene, constituted my ground state, and my excited state will be where one of the electron from AU has moved to B2G, correct? So this particular system has the symmetry of if I remember my previous condition, that whichever orbital is doubly occupied, I do not worry about that because that will give me totally symmetric IR. So I will only consider this orbitals which has the unpaired electron. So therefore this part is redundant to me when I try to find out the excited state. So then I have this AU and I have to take a direct product of AU to B2G. Now this A2U to B2G, that gives me which particular IR. So in that case, I can easily take a look at my character table, and I can see that AU and B2G gives me B2U. So this gives me a direct product which is B2U, right. So we already know how to get these direct products, right. So B2U is my first excited state, right. So this is my ground state, and this is my first excited state. Now similarly, what I can do, I have to find out what happens to the symmetry of the state when I have a transition from here. So instead of this, if I have a situation where this electron is taken to this orbital, while this one it remains as such. Okay. So this orbital is now occupied by a pair of electrons, while B1U is singly occupied and B2G is singly occupied. So here what I have to do, I have to worry about direct product B1U and B2G. So if you have a look at the character table, carry out the direct product, you will see that this gives you B3U. All right. So this is my next excited state. Okay. So if I call it a second excited state, then I have to worry about the other one. So that is AU to B3G. So if I have one electron transferred to B3G from AU. So this also supposedly having the same energy as that of this particular transition, which gives you B3U. So for this particular transition from AU to B3G, the symmetry of the state will be obtained by taking a direct product of AU and B3G. And here, after doing this, you will see that this corresponds to again B3U symmetry. Okay. So you can say that this is also almost like degenerate with the previous excited state that we got. So now if I want to find out the whether or not the transition from AU to B2G or AU to B3G or B1U to B2G, they are allowed or not, I have to actually find out whether a transition from AG to B2U or AG to B3U are allowed or not. So in the next step, what you have to do, you have to solve this problem, that is you have the excited state having symmetry B2U, and you have to take a direct product with the Cartesian coordinate system. So if you look at the character table for D2H, then you will see that Z transform as B1U, Y transform as B2U, while X transform as B3U. Okay, these are the irreducible representation. So you have to have B1U, B2U, B3U. So and then you have this AG, which is a totally symmetric IR and represents the ground electronic state. So what you can do, you since this is totally symmetric irreducible representation, you do not care about this one. So you find the direct product between B2U and B1U, B2U and B2U, B2U and B3U. So immediately you can see that the second integral, that is B2U and B2U direct product, it will definitely give you AG, right? So therefore this transition with respect to y is allowed, correct? So here you can cross check what will happen if you multiply B2U and B1U. So if you look at the character table, then you will see that B2U and B1U will not yield AG upon direct product. And what about B2U and B3U? That is also not going to give you the totally symmetric IR. So only the transition is allowed overall, and it is allowed in y direction. Why? Because this B2U, this has y as its basis. So this particular transition will be y polarized. Now for the other two transitions, you have the same type of situation where you have B3U as the irreducible representation for both the excited states, and you have the same situation here, B1U and B2U or B3U, and then you have AG, correct? So obviously you can see that B3U and B3U direct product that is going to survive because that is going to give you the totally symmetric irreducible representation. And if you check the character table, what you will see that the direct product between B3U and B1U or B3U and B2U will not give you AG. So any irreducible representation that is not totally symmetric IR is not going to give you non-zero value for the overall transition moment integral. Now B3U, I can see that forms the X forms the basis for B3U, okay, or X transform as B3U. So therefore again for this transition, that is first transition, this one, it refers to a transition from here to here. The second transition refers to the electron making a transition from here to here, and the third transition, it refers to a transition from here to here. So first one, we see that this is y polarized, while this one I can see B3 transformed as X transformed as B3U. So therefore this transition overall allowed, and specifically this transition is X polarized, right? So if I have to mark here, so this transition is y polarized, while these two are X polarized, both of them. So this as well as this, both of them are X polarized. So in this way we have learned about how to find out about the allowedness of any particular transition from one given orbital to another orbital, and we also learned how to find the symmetry of the state as a whole, because at the end when you want to find the selection rule, you need to work with the state, not with the orbital symmetry, right? So you first find the symmetry of the state, find out the symmetry of the orbital, and assign the electron symmetry to the electrons in those orbitals, and then ultimately find the symmetry of the overall state, and then use that to form your transition moment integral, find the direct products, and you find out whether that contains totally symmetric IR or not. If the answer is yes, transition is allowed. If it is not, transition is forbidden. If it is allowed for in one of the particular direction or in a particular plane, then we know that this is either polarized in that particular direction or that particular plane. So we found here that the lowest transition is allowed, and it is allowed in the y direction, while the other two, the next lowest transition, they are allowed in x direction. So in the following class we will try to get some more examples and explain these things. so that the overall this the particular case of electronic spectroscopy and how we use group theory. Here whatever we did, we actually we did not do any hardcore mathematics here, okay, to find out whether the integral will survive or not. All we used the symmetry concept, right? We added the symmetry concept here to this electronic states, and ultimately figured out without going into the detail of mathematics whether it will survive or not, right? So now suppose a particular transition is allowed, so you will get the spectra, correct? You are talking about suppose you are talking about electronic transition, so you will get an electronic spectra, so probably in the visible range or in the UV region of the spectra. Now what will be your intensities? So the intensity will depend on how much allowedness an overall electronic transition is. What is the meaning? So if you remember, we had these three integrals, Frank-Condon factor, and we had this transition between two electronic orbitals and the spin overlap. So if a particular electronic transition is spin allowed but it is orbitally forbidden, then its intensity is very very low, and intensities are expressed, I mean it's very easily you can talk in terms of the extinction coefficient. So the extinction coefficient will be very very low for orbitally forbidden transition. Now a spin forbidden transition, so for which this psi star s prime psi star, this integral is 0, while the orbital in the integral is non-zero, meaning that it is orbitally allowed but it is spin forbidden. In that case its intensity will be moderately higher, and that will be reflected in its extinction coefficient, right? Now when both the transition is both spin allowed as well as orbital allowed, then we call it is totally allowed system, or if both of them are forbidden, then we call it totally forbidden system. So for a totally allowed system, the band will be extremely bright. And then what does the Frank-Condon factor do here? So Frank-Condon factor, it dictates like how much is the overlap between two vibrational states involved in an overall electronic transition. So the better the overlap, better is the probability of transition, correct? So if there is no overlap, then it's 10 to 0. So this Frank-Condon factor, it modulates the intensities of an electronic transition. Suppose I have a totally allowed transition, meaning that it is orbitally allowed and also spin allowed, then Frank-Condon factor will modulate the intensity. So for a particular vibrational transition within the electronic levels, for which the Frank-Condon factor is higher, it will have higher intensity for the particular band I am talking about, while a lower Frank-Condon factor will yield lower intensity overall. So essentially that Frank-Condon factor will modulate the overall electronic absorption intensity. So with this we will stop here today, and I thank you very much for your attention.